Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast of Organic Chemistry lectures and solutions to homework problems. In today's Scribblecast, we're going to be examining the topic of stereochemistry. Stereochemistry is the study of molecules in three dimensions. We're interested in understanding the structural relationships of the atoms as they exist in three dimensions and how they account for the physical behaviors and chemical properties of those molecules. Now recently we have defined the relationships of different molecules referred to as isomers. It turns out that isomers actually come in a wide range of categories, not as simple as has been previously discussed. Now we've already defined isomers as non-identical compounds that possess the same molecular formula. Non-identical compounds that possess the same molecular formula. The example we looked at previously was one special type of isomer. And the one we looked at had the molecular formula C2H6O. And the two examples of isomers that had this molecular formula were the molecule dimethyl ether, where two methyl groups are bound to an oxygen, and the molecule ethanol, or ethyl alcohol, where an ethyl group is bound to an OH. Now these two structures are very different. The actual arrangement of the atoms varies so that you generate different structures, different functional groups. They both possess the molecular formula C2H6O, but structurally they're very different. And because of this, they were referred to as structural isomers, a special subset of isomers. Now, structural isomers actually differ in the physical arrangement of the atoms so that different functional groups and different structures are achieved. Now, you may not always get different functional groups, but the actual physical arrangement of the atoms will be different. Not all isomerism is structural isomerism. In some cases, you can get isomers that are found within the same structure. For example, conformational isomerism deals with isomerism within one molecule. Conformation. Conformational isomers. This is isomerism that results because of rotation about a single bond. It occurs because of bond rotation. Let's consider a simple example. Let's consider the molecule ethane. But in this case, I'm going to draw it a little differently than you've normally seen it. I'm going to draw it in a pattern that is referred to as a sawhorse diagram. Now what's interesting is one could ask the question as to why I drew the ethane with the arrangement of hydrogen atoms that you see here. For example, if I keep the back hydrogens in the same position, one could ask the question, why did you not draw it so that the hydrogens on the front were different, in different positions, maybe drawn thusly. The only difference between these two structures is I have rotated the H's slightly. I've rotated, if you like, around the carbon-carbon sigma bond. Taken this methyl group and actually rotated it. Now, in actual fact, the molecule is still ethane. They're not structurally different, but the arrangement of the H's relative to each other have changed. So what I've really drawn is the shapes that can be achieved in the ethane molecule by rotating about the carbon-carbon single bond. Now, we could take note of this if I look at these H's, where I'm drawing the dashes. These H's seem to line up perfectly. Because of this, this conformation is said to be eclipsed. An eclipsed conformation. The hydrogens are said to be eclipsed. Whereas, in this conformation where the hydrogens do not align, but the hydrogens actually fall in between the positions of the hydrogens on the other carbon, the hydrogens are said to be staggered between each other. Now, in actual fact, at room temperature, the carbon-carbon sigma bond can rotate, and there's more than enough energy at room temperature for it to rotate right through the eclipsed and staggered states. So, conformational isomerism is very different from the structural isomerism we've seen previously. Structural isomerism actually generates distinct structures, different molecules, sometimes different functional groups. But conformational isomerism is the change in structure within a molecule itself caused by bond rotation. Now, we're going to examine this much more closely a little later on. But right now, I'd like to continue on looking at different types of isomerism. The next one we want to look at and spend some time on is called geometric isomerism. Geometric isomerism. Now, geometric isomerism is the isomerism that results due to hindered rotation. So let's write that down. Hindered rotation. And in order to describe hindered rotation, I want to begin with a consideration of the nature of the carbon-carbon double bond. And I'm going to look in the most simple of cases, the molecule ethene, which has a C double bond C. Now I'm going to redraw this showing the 2p orbitals. So the lines represent my sp squared orbitals, if you like. The blue line's my sigma bond to the other carbon. And I want to show the interaction of the 2p orbitals. So I'm going to draw, using a different color, my 2p orbitals. One 2p and the other 2p. Now what's interesting is the nature of the second component of the double bond is the side-to-side overlap of the 2p orbitals, or what we refer to as the pi bond. Now, the pi bond forms because of side-to-side overlap. However, if we attempt to rotate now about the sigma bond, rotating one of the carbons, the 2p orbital will rotate out of alignment with the other 2p. And that would break the pi bond. Now, bonds are relatively strong, and in order to break the pi bond, one must input a lot of energy, greater typically than what is available at room temperature. In fact, we're probably talking over 100 degrees Celsius. So this rotation is hindered. Now, when you have 4 identical groups around the carbon-carbon bond, as you do in ethene, this hindrance doesn't lead to any isomerism. But if we examine another alkene, this isomerism, geometric isomerism, becomes very important. So I'm going to draw this molecule twice. Here we go. And I'm going to name it. Longest carbon chain is 1, 2, 3, 4. A 4-carbon alkane is a butane. With the double bond in it, becomes a butene. The double bond is located at the second carbon. So this is a but-2-ene. Likewise, this molecule is also a 4-carbon alkane with a double bond at position 2. So it is also but-2-ene. Okay. Now what's interesting is if I compare the two structures, I could turn the first structure, this structure I'm going to call A, structure A, into structure B if I could rotate around this double bond. If I could take the one end of the molecule and flip it, I would get structure B. But such rotation, as we've already stated, would break the side-to-side overlap of the 2p orbitals. And that takes more energy than is available at room temperature. Because the double bond is present, the rotation is hindered. It's prevented. And structure A cannot rotate to form structure B. Now, structure B is different than structure A. The CH3s on opposite sides of the double bond, whereas in structure A we have the CH3s on the same side of the double bond. This chemical difference, this arrangement in space of the atoms in the molecule in a different way, leads to different chemical and physical properties, different melting points, boiling points, different behaviors in reactions. Essentially, they are different molecules. But they are different molecules because the rotation about the double bond is hindered, so they're referred to as geometric isomers. However, how are we going to distinguish between them? If they are both but-2-ene, or 2 butenes, the names are identical. There's no way to distinguish between them. So we need a nomenclature we can add to our IUPAC nomenclature to allow for this hindered rotation, this geometric isomerism, to be described. That description is when the two identical groups, the two methyls are on the same side, it is called cis, C-I-S, and you separate it from the main word by a hyphen, cis, butene. But when the identical groups, the two methyls, are on opposite sides of the double bond, it is called trans. And there you have trans and cis butene. Okay, as I indicated, geometric isomers have different physical properties and different chemical properties. But what are the requirements to have this type of geometric isomerism, this hindered rotation? Well, in the double bond, let's examine what is required. We first looked at the molecule ethene. The molecule ethene does not have this type of hindered rotation effect. Or I should more accurately say, although the rotation is hindered, hindering rotation when there's identical groups produces no differences. There's no ethene I could draw which has different groups on one side of the double bond. Essentially, even though the bond has hindered rotation, there is no geometric isomerism. Well, what if I had this molecule, where at one end I have two different groups? That is here, you see a methyl and an H, but on the other side you see two H's. If I examine this and ask, can I produce any different structures? The truth is, I can take the whole thing and flip it. But the truth is, they're always the same. No matter which way I draw this thing, all I'm doing is picking up the whole molecule and flipping it over. I'm not changing the molecule at all. I'm not breaking any bonds. All these three structures are identical. All I've done is pick this guy up and flipped him over. If I flip him over this way, take that end and just flip it right over, I get this molecule. If I flip it over from top to bottom, just pick up the whole molecule, flip it, I get this guy. These structures are all the same. So I see I have no geometric isomerism if I split the double bond and I look at these two groups. They're different. But if one side has two groups that are the same, I do not get the geometric isomeric effect. In order to have geometric isomerism around the double bond, I have to have, off of one carbon, two different groups. There. So, if I look at this, those two have to be different, and I have to have two different groups on the other carbon. If these two are different, and these two are different, then I can have geometric isomerism. Notice this way they can be the same. Two methyls. But off of the one carbon of the double bond, the two units attached to that one carbon must be different. And then the two units attached to the other carbon off the double bond must be different. All right. So to get this geometric isomerism off of a double bond, we must look at one carbon of the double bond, see that two groups are different. Look at the other carbon of the double bond, see that we have two different groups. Then we can have geometric isomerism. Are there any other examples of this geometric isomerism? Well, it turns out this hindered rotation can also occur in cyclic rings. Consider this molecule, cyclobutane. And let's draw two methyls off of the cyclobutane. Let's name this molecule. This molecule is 1,2-dimethyl cyclobutane. Now let's take this ring structure, and we're going to assume it is flat for simplicity's sake. And let's draw it tilted on its edge so you see a more edge-on view of the four-membered ring. And I'm going to draw the group straight up and down just to exaggerate things. And so I could draw my 1,2-dimethyl cyclobutane this way. Let's draw the ring again. And I could also draw 1,2-dimethyl cyclobutane this way. Now, what's interesting about these two structures is that once you have a four-membered ring like this, and you have the group on one side of the ring, there's no way to rotate around the ring that will allow the CH3 to flip up. If I simply take the whole ring on this structure and flip it upside down, I simply get the same thing. Well, what do I see? Maybe I should make that bond taller. Just stick it right up here. What do I see? Both methyls above the ring now, where they were below. But the point is, both methyls are either below or above. They're always on the same side of the ring. I never, just by moving this molecule, can change it into this structure. That is, the structures I've drawn of A can never be turned into B without breaking bonds. Because it can't be interconverted, the rotation about the bond is hindered. The methyls are locked into position. They're locked into the same side. And in A, since they're locked in the same side, this structure is called cis. And so it would be cis-1,2-dimethyl cyclobutane. Structure B would be called trans 1,2-dimethyl cyclobutane. So geometric isomerism can occur in double bonded systems, molecules with double bonds, or molecules that are ring structures, molecules in rings. And why do both these structures work? Because they both give you hindered rotation. Okay. So what we want to do now is look a little more deeply into the nomenclature of the double bonded system of geometric isomers. I'm going to draw a structure, and I wish you to determine if this structure can have geometric isomerism. Okay. What I want you to do is determine, can this structure be drawn in a way that's different so that you can have geometric isomers? If you remember our test for geometric isomerism, we essentially split the molecule. And we look at one side first. We look at this carbon and we ask the question, are the two groups off of that carbon of the double bond different? Is the CH3 different from the Br? And the answer obviously is yes. Now we look on the other side, the other carbon, and we ask, is the fluorine different from the hydrogen? And the answer is obviously once again yes. Since both carbons of the double bond possess groups that are different, this molecule can have geometric isomerism. So why don't we name the molecule and generate an IUPAC name for it? Well, I find the longest carbon chain with the alkene in it, and that's 1, 2, 3. So I have a 3-propene or prop-3-ene. Prop-3-ene. Very good. And I count in, sorry about that, prop-3-ene. Well, is there a lower numbering scheme for that? Obviously there is. Alrighty, so we have to pay a little more attention, watch both sides of numbering. 1, 2, 3, we could give that a 1, which would be a lower number and better. So here's a prop-1-ene, not prop-3-ene. The fluoro is at 1 and the bromo's at 2. Alphabetically, the B comes before F, so we have, it looks like, a 1 fluoro and a 2 bromo. 2 bromo. So we have a 2 bromo, 1 fluoro, prop-1-ene. Now the question is, if I remember my geometric isomerism nomenclature properly, to determine whether it is cis or trans. Okay, so let's hide these numbers. And ask the question, are the two CH3s on the same side? Oh, wait a second. There's only one CH3. Okay, how about the two Fs? Are they on the... Oh, there's only one F. Wait a second. How do you tell who's on the same side and who's on different sides? Clearly, in this case of geometric isomerism, the simple cis-trans nomenclature doesn't appear to work. We don't have identical groups off the side, so we can't say, for example, the CH3 is on the same side as CH3. We could say the CH3 is on the same side of F. It's on the cis side of F, but it's trans, or opposite side to H. The Br is trans to the F. How do you determine? By what rule can we judge how we're going to reference where the groups are? Well, we're going to use a prioritization scheme. I believe it's called the Kohn-Ingold prelog system, or what more simply is referred to as the EZ or EZ nomenclature system for alkenes. This nomenclature system has a set of rules. You implement these rules in the order that they appear. The first rule is paramount, and you only go to subsequent rules if the first rule doesn't work. What is that first rule? Well, the first rule is that the highest atomic number receives the highest priority. So, the highest atomic number receives the highest priority. So just by way of example, if I was looking at halides, because iodine's higher atomic number than bromine, iodine would get higher priority, would have greater priority than bromine. His atomic number is higher than chlorine, so he'd get greater atomic priority over chlorine, who would get greater priority over fluorine. Now let's apply this to a structure. If I again split the molecule in two, and looking at the left-hand carbon of the double bond, that's this guy, who is higher atomic number, bromine or carbon? Well, clearly the bromine is higher atomic number. Now I look at the other side of the double bond, this carbon with the arrow. And I ask the same question, who's higher atomic number, fluorine or hydrogen? Well, the fluorine's higher atomic number. Okay, and then I ask a simple question. Where along the double bond, relative to each other, are the high priority groups? Are they on the same side of the double bond, or are they opposite sides of the double bond? So I'm effectively splitting the double bond this way now. Well, I see the fluorine is on the other side of the bromine. They're on opposite sides. The nomenclature that is used here is we use E to mean opposite. Apparently, I've been able to discern that the E comes from the German entgegen, meaning opposite. If the priority groups were on the same side, we use Z, which comes from the German zusammen, which means the same side. So how would I incorporate this into my name? Well, I do it thusly. I would write in this structure E and then a hyphen, 2 bromo, 1 fluoro, and the proponene. Okay. Let's take a look and try applying this rule number 1 to another structure, if we could. Let's try it with this molecule. Wow, what is that? Is that a D? What element from the periodic table has the symbol D? Well, in actual fact, what I'm using here, or drawing here, is D for deuterium. Deuterium is a hydrogen atom, but it has a neutron in the nucleus, not just a proton. So deuterium is an isotope of hydrogen. It is not a single proton in its nucleus. It has a proton and neutron. And if we apply rule number 1, in fact, before we do that, why don't we generate the IUPAC name for this? Well, again, we have a 1-propene. So there is a proponene. And we have a 2-bromo. But what do we call the D? Well, what we can call the D is a deutero. So we have a 2-bromo, 2-bromo, hyphen, 1 deutero. Maybe I need more room than that. 1 deutero. So 2-bromo, 1 deutero, proponene. Okay, interesting. What do we do with this? How do we prioritize? Try applying rule number 1 again. We see that we have different groups. We have a C off the double bond, which has bromine and methyl. And the other C of the double bond has an H and D. And the H and D are different atoms, even though they're isotopes. Because of this is geometric isomerism. But if we apply rule 1, it says use atomic number. Well, the bromine's higher atomic number than carbon. But hydrogen and deuterium both have only 1 proton. They both only have an atomic number of 1. So we need a second rule. We can't distinguish with this first rule. And the second rule simply states that if you have two isotopes, the isotope of higher mass or higher mass number, higher mass gets the higher priority. Okay, I can live with that. So in that case, deuterium, which has a proton and a neutron, has greater mass than a hydrogen, which has a proton. And so now the priority groups are on the same side. And in this case, same side means Z, so Z would go in front, designating the geometric isomerism of this molecule. Very good. Let's try another case. What about this case? How's that? And let's finish labeling it properly. Does this molecule have geometric isomerism? Well, once again, we must look at the carbon with the double bond and focus on one end. If I focus on the left-hand carbon, this guy, then I see I have an ethyl attached to it and an isopropyl group. Well, they're two different functional groups, so yes, there are two different groups off that carbon. Let's look at the other carbon of the double bond. We see that this carbon has a propyl group off of it, and what is that group? Do you remember? We've pulled an H off of the tertiary carbon of isobutane and attached it here. So it is called a tert-butyl group. A tert-butyl is different from a propyl. So this carbon has two different groups. So indeed, there's geometric isomerism here. Now you'll notice when I'm trying to determine EZ nomenclature, if I'm asked to name the molecule with EZ, the first thing I always do is get the IUPAC name. And in fact, I wouldn't even worry about EZ isomerism until I've got the IUPAC name, if I'm asked to name the molecule. So if I number, find the longest carbon chain, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Oop, there's two different 7-carbon chains. I can either go up here, or I can sort of loop down. When two chains are identical, you pick the chain with the most substituents. If I go straight up, I've got the isopropyl and the tert-butyl substituents. But if I loop down, I have a methyl, an ethyl, and the tert-butyl. And that's 3 substituents. So I'm going to loop down. Now, which end do I number from? It's the one that gives me the lowest number to the alkene, the priority group. So I've got a 1, 2, 3, 4, 5, 6, 7. So what I have here is a heptene, a 3-heptene, or a hept. Ene. Okay, now we can name some substituents. Well, if I number, I have 1, 2, I have a 2-methyl. I have a 3-ethyl. And it looks like I have a 4-tert butyl. So there's a hyphen and butyl. Now for alphabetizing, I use the M, the E, and the B. Because the tert's hyphenated, it's not used. So for alphabetizing, it looks like B is going to come first, then E, and then the methyl. So I'm going to have a 2-methyl, a 3-ethyl, and then finally a 4-terbutyl. So a 4-terbutyl. So 4-terbutyl, 3-ethyl, 2-methyl, hepthrene. Okay. Well, now all that remains is finding out the EZ nomenclature for this molecule. And the way you do that is to prioritize around the double bond. So I look at this carbon first, and I want to determine priority. So I apply rule number 1. Rule number 1 says look off the carbon of the double bond and compare the atomic number. Well, carbon, carbon. Carbon has identical atomic number. Doesn't help us. Okay, rule number 2 states the isotope of greater mass gets priority. Well, there's no different isotopes. Carbon and carbon. They're identical again. So it looks like we need a third rule. What's rule 3? Rule 3 simply states that if you have identical atoms of atomic number, proceed out the chain. Out or down, out the chain. To the highest atom possible. And compare. Atomic numbers. What does that mean? Well, what it means is, look, I'm going to dot the 2 carbons. Those 2 carbons are tied. Absolutely. So you proceed out the chain. That is, I'm going to go to this carbon. Now you say, hold it. Why did you proceed out to that carbon when it has 2 hydrogens? Well, I go to the highest atomic number first. Carbon's higher than hydrogen, so I proceed out the chain. I check this carbon. This carbon, I'm going to proceed out the chain to that carbon. And I'm comparing a carbon now to this carbon. That's tied. So I go back to my original. All right? So we've done one jump, and we haven't helped the situation. Now we proceed out to the next highest atom. Well, we've already gone to the carbon, so you've just got 2 hydrogens here, so you jump to the hydrogen. This guy can jump to this carbon. You proceed out the chain and you look at that carbon. This case, we're comparing one of these hydrogens to this carbon. Well, carbon's higher atomic number, so this group gets priority. So you proceed out the chain, first point of difference. Let's do it on the other. Let's do it on this guy. Well, I'm comparing initially this carbon to that carbon. And they're both carbons, so they have the same atomic number. So we proceed out the chain. Well, the highest atomic number further out the chain from this carbon is that guy. And I could jump to this carbon. Well, then I'm comparing a carbon with a carbon, and that's identical, so I go back to my original carbon, and I say, okay, I'm going to jump to the next atom attached to it. Well, that's an H. In this case, is a carbon. This carbon is higher atomic number than the H, so I found my first point of difference. And what do I get? This trip-butyl, this priority. So, since the priority groups are on opposite sides, this becomes E. E, 4-terp-butyl, 3-ethyl, 2-methyl, hep3E. Now, I want to point out something. Sometimes you will see examples that show, for example, a chlorine, which is a very high atomic number compared to carbon. And if there was a chlorine here, and I was doing this side of the molecule, and I'm comparing carbon-carbon, when I jump to the first carbon, I jump to a chlorine. Well, chlorine's higher atomic number, so this group would have been priority. Let's make it a CH3 again. But I just want to point out, you can't always just say, oh, there's a chlorine on the chain, it must be highest priority. Why? Suppose this last CH3 wasn't there, it was a chlorine on the end. You could not say this group is highest priority, because watch what happens when we use our proceed out the chain rule. We've got the two dots showing our carbons that we're comparing. Both are carbons, they have the same atomic number. Now, we're going to compare the first atom. Well, the first atom I hit when I proceed out the chain is a carbon. This guy hits carbon, so we're tied. So we go back to our original carbon. We've jumped. Now we jump to a different atom. Well, we can jump to this carbon. This guy now has to jump to an H. The carbon up here is a higher atomic number than the H. Notice we did not get to the chlorine yet. So this is still higher priority than the CH2CH2Cl because you didn't reach it. You didn't proceed out the chain far enough. And so in this case we would have E. So be careful. Don't just say there's a chlorine there. It must be higher atomic number. All right. Before we do some examples, there's one more rule we have to look at in this nomenclature of geometric isomers. And that's what happens if there's multiple bonds present in the molecule. Suppose I have this molecule. Let's do the IUPAC name of this molecule. Find the longest carbon chain with the highest priority group. Well, the carboxylic acid is the highest priority group. I number the chain 1, 2, 3, 4, 5, 6, 7. I have a heptanoic acid with an ene in it, a double bond, so it's 2-heptene or hept. 2-enoic acid, and the acid's a separate word. Now I have some substituents. Off of the fourth carbon I have an oxo. Off of the third carbon I have an ethyl. And off of the second carbon, I have a CH2OH. Now, what are we going to call that? Well, there's no simple name for the CH2OH, so we have to use the IUPAC substituent naming system, which says you number a chain from the point of attachment to the main chain. Well, this carbon chain is just one, so that makes it a methyl. And off of the methyl, we have an OH, which is a hydroxy. So at carbon 2, I have 2 bracket a 1-hydroxymethyl. And that's all one word, hydroxymethyl. Okay, no spaces, and it's in brackets. Now for alphabetizing, I'm going to be fairly lenient in the course for things that come in brackets. Alphabetizing, we use the O, we use the E, but do we use the H or the M? And honestly, I'm going to be lenient on this aspect of the course. You may use either the H or the M. In this case, it makes no difference. Both H and M fall in between the E and the O. So, looks like we're going to have a 4-oxo here. And then we're going to have the 2 bracket 1-hydroxy. I'm going to need more room than that. Okay, let's take it right over then. 2 bracket 1-hydroxy. Is the 1 needed? Well, since it's a methyl, probably not, but I don't know if I'm going to be able to fit the methyl in. Well, probably not. That's my bracket. Let's squeeze that 4 in a little smaller. There we go. Okay, and then we have the 3-ethyl, and I'll put that up here. 3-ethyl. So the name of this molecule is 3-ethyl hyphen 2-1-hydroxymethyl 4. There should be a hyphen after the bracket. Let's try to make that a little clearer. Make this a little smaller. 4-oxo. So 3-ethyl, 2-1-hydroxymethyl, 4-oxo, heptuenoic acid. Now, let's attempt to apply our Z nomenclature prioritization rules. Let's first check, do we have geometric isomers? If I split the molecule this way and look on the left side, the carbon of the double bond, look at the 2 groups, are they different groups? And the answer is yes. If I now look at the other side of the carbon, the double bond, the right side, I see a carboxylic acid and the CH2OH. Are they different groups? Yes. So this molecule has geometric isomerism. Now, what happens next is an attempt to prioritize the groups. And if we apply rule 1, well, off of this carbon, the left-hand carbon, we have 2 carbons. So they have the same atomic number. Rule number 2 looks for isotopes, doesn't help us. Rule number 3 says proceed out the chain, but I've got a problem. I've got a double bond here. How do you proceed out the chain for a double bond? Does it count anything special? And rule number 4 simply states that multiple bonds are treated as single bond equivalents. Equivalence. What does that mean? Well, it essentially means that if you had, and let's just try something that we don't have here. If you had a C triple bond N, let's say, and I was going to proceed out the chain, I would treat that as if it was a C attached to 3 N's through single bonds. That is, when I proceed out the chain, and I get no difference and I have to go back, I can go out a triple bond 3 times. I can count it as a single bond. Double bonds, you can proceed out twice. So let's try doing it and see what it looks like. So as I said, I'm looking at these 2 carbons where I put the dots. I'm going to proceed out the chain. This carbon, if I proceed out the chain to the highest atomic number, I go to this carbon on the CH3. Now, when I proceed out the chain of this carbon, okay, do I go to the carbon? No, you go to the highest atomic species off of this, and oxygen has the higher atomic number, so I proceed out to oxygen. Now I only have to go out once because oxygen's higher atomic number than C, and so I now know that this guy's higher priority. Let's try at the other end now. Let's look at these two carbons. Well, they're both carbons, so they're tied for atomic number. I can proceed out the double bond O once and hit an oxygen on the top benzoic acid. The CH2, I can proceed out and hit an oxygen on the hydroxyl. That's the highest atomic number group attached to CH2. So we're tied. So we go back to our carbon again, and we do it again. Because there's a double bond, I can go out the double bond a second time. It counts as two single bonds. This carbon, though, I've already been out to the oxygen, so the only thing it has off of it is H's, so I hit an H next. Oxygen's higher priority than H, so now we have a point of difference. I can asterisk this. My two asterisks are opposite sides of the double bond. I mean, when I say opposite, I'm talking about in this plane. Okay? And so opposite side gets an E. And so there you have E3-ethyl. Okay. Let's try one of these and see what we can come up with. So what I'm going to do here is I'm going to draw a molecule, and we're going to name it. Okay. Right, so here we go. And the first thing we're going to do, you get a question, let's say, that says name this molecule and provide its absolute configuration. When you hear the term absolute configuration, it means give the stereochemistry, the EZ nomenclature for it. And the first thing you do is ignore that and just get an IUPAC name. Find the longest carbon chain with the highest priority groups. Well, let's start. We could number this guy 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. If I go this way, I get 1, 2, 3 substituents. If I go this way, I get 1, 2, 3 substituents. The number of substituents tied. Since the alkene's higher priority than the alkyl, I'll include it in the root chain. All right. When numbering, there's an exception to the prioritization rule. If there's just enes and ynes, count the yne equivalent to the enes and go for the lowest number. If we go this way, we get 1, 2. We hit a 9 at 2. If we start this way, we start at 1. So I'm going to obviously start this way. 1, 2, 3, 4, 5, 6, 7. So what I have here is a 7-carbon alkene, that's a heptane. With 2 enes, it's heptadiene. 1 yne, that's heptadiene-yne. The 2 enes are at 1 and 3, so it's hepta. I'm not going to have enough room there. I'm going to have to go a little more over. Let's try this. Hepta 1,3-diene and a 5-ine. Okay, so we have hepta 1,3-diene 5-ine. Off of carbon 3 or 2, we have a methyl. Excellent. Off of carbon 3, we have an isopropyl. Off of carbon 4, we have a tert-butyl. Tert-butyl. If I'm going to alphabetize, I use the M, the I, and the B. So it looks like I'm going to have a 3-isopropyl. With a 2-methyl. And then up here, it looks like we get the 4-tert-butyl. So 4-tert-butyl hyphen 3-isopropyl 2-methyl hepta 1,3-diene 5-ine. Okay, so now we're ready to look for geometric isomerism around our double bonds. Uh-oh, I see a problem. We've got 2 double bonds. Oh my. Wait a sec. If we split this guy and look at the carbon on the left side, we see he has 2 identical groups. And if there's 2 identical groups off one of the carbons of the double bond, you don't get geometric isomerism. Whew. That was a problem there for a second. Okay, what about this side? Well, now we see we've got quite a bit. If we look at this carbon here, we've got 2 different groups, so there is the possibility. Look at the other side, we have a tert-butyl and an alkyne. That's 2 different groups. We have geometric isomerism. So let's look at this carbon again and look for differences in atomic number. We've got a carbon and a carbon, the tied, so I proceed out the chain. We hit a carbon, we hit a carbon. Okay, that's no good, so I go at the chain again from the carbon. This time I go that way, I hit a carbon. I could go at the double bond a second time. I hit a carbon. Still tied. The next thing proceeding out the chain is I hit a hydrogen off the carbon. I hit a carbon. Carbon's higher atomic number than that hydrogen. So this guy is top priority on that side. Okay, let's do it on the right-hand side. What do we have? We have a carbon of a tert-butyl right here, and a carbon of the alkyne. So we're tied. So we got to proceed out the chain. So I go out here first, go down the double triple bond. Carbon, carbon, we're tied. Okay, let's go back. Let's try it again. Well, let's go out to the other carbon here. It's a triple bond, so let's go down the triple bond a second time because it counts as single bond equivalencies. And again, still 2 carbons. We're tied. Ooh. Okay, so I'm going to proceed out the chain to the other carbon. Go down the triple bond one more time. Still tied. So now that we're tied, we've got to move down the chain. So this guy, I'm going to be using this as the carbon. Since they're all methyls, I have to go out one. If they weren't methyls, I'd go down the longest chain, but I'm proceeding to just one of the methyls now. It doesn't matter which one, so let's use this one. So this carbon has a carbon attached to him, and we're proceeding outwards always, and he has a hydrogen. So we've hit our first point of difference. This carbon wins out, higher atomic number than hydrogen. So this group. So there you have it, and what we get is E. It's on opposite sides of the double bond. Okay, but what would have happened? What would happen if we were naming this molecule? And this double bond had turned out to be able to have geometric isomerism. Let's give it that. Let's change this H to a CH3. What that does is add one carbon. If I'm numbering it, now I get 1, 2 with the ine, 3, 4, so it's a 2, 4, 5, 6. It's 2, 4, 6. If I go this way, I get 1, 2, 3, 4, 5, 6, 2, 4, 6. The only difference is, do I want to give the ine the 2 or the ene the 2? Now, if it's exactly the same in tide, because alkene's higher priority, I would probably give the ene the number 2, which means I would number this way. Now, all I've done, therefore, is add one extra carbon. 1, 2, 3, well, let's number it. 1, 2, 3, 4, 5, 6, 7, 8. So my heptadiene has become an octadiene. Okay, so I can write that, octa. It's not 1, 3 now, it's a 2, 4 diene, 6 ine. Okay, I can handle that. So there we are. And I have the exact same substituents. They've just increased to one number. My 2-methyls become a 3-methyl. My 3-isopropyls become a 4-isopropyl. My 4-tert-butyl has become a 5. So essentially I have a 4-isopropyl, 3-methyl, and then my 4-tert-butyl is now 5-tert-butyl. So adding the 1-methyl at that extra position has just slightly changed my name. But now here's the problem. We've got geometric isomerism at 2 double bonds. How do you handle this? Well, once you've named your structure using IUPAC nomenclature, what you do next is just focus on the double bonds individually, one at a time. So I'm going to focus, let's take these numbers out because they get a bit confusing if you got too many numbers. I'm going to focus on the double bond here. And what I'm going to do is I'm going to change color. And I'm going to ask, using our rules, do we have geometric isomerism here? Do we have, off of this carbon here, do we have different groups? Well, H and CH3 are different. And so we've got a CH3 and this huge monstrosity. Well, the CH3 is different from the monstrosity, so you got different groups. So yes, it's geometric isomerism. So let's look at the one on the left and prioritize. Who's higher priority, an H or a CH3? Well, by atomic number, carbon is higher atomic number than H, so it's higher priority. So on this guy, we have highest priority in red there. Now let's look at the other carbon. We have the CH3 and the monstrosity. Well, clearly the C's are tied, but if I proceed out the chain, on the CH3 I hit an H. On this guy I hit a carbon. So clearly right here is my priority, and we see the 2 priority groups on the same side of the double bond. So this double bond becomes Z. Now let's try a different color. Let's use black. And now we're going to do it for this double bond. So we're going to split our double bond. We're going to ask the same question. We're going to look at this carbon first and look at its 2 groups. Now we did this prioritization once already. I'll remove that red because we know this guy's Z now. And we did already, so let's do it again in case you missed it. We have this carbon and this carbon. We proceed out the chain to a carbon. Okay. Proceed out the chain to a carbon. Well, the 2 carbons are still tied, so we go back to our original carbon. We proceed out the chain. This is double bond, so we can go again. We go out here to the other carbon. Still tied, comparing 2 carbons. So we go back to our original atom. We've already gone on this guy to both methyls, so now we have to go to the H. This guy has a third carbon. So we're comparing this carbon to this H. Okay. So clearly, on this, the upper group over here is higher priority. Okay, now let's take a look at this guy, this carbon. Well, those are his two carbons. They're tied. Proceed up the chain. Well, we're going to go again. Carbon, carbon. Doesn't help me. Go to the next carbon. We'll go down the triple bond again. Still carbons are tied. Doesn't help me. Go back. Go out the third carbon. Go down the triple bond a third time. Oh, still tied with carbon. Okay. So now I move down the chain in my reference. This one, the three identical methyls, I can go to either one. If there was one that was longer, I would go down that longer chain. What do we have here? Carbon. Proceed out the chain. I hit a carbon. This guy hit an H. At last. This group's higher priority. First point of difference. And our two black asterisks on opposite sides of the double bond. So our black guy is E. Now the question is, how do you designate this in the name? Okay, so let's remove those. How do you designate that in the name? You've got a Z and an E. How are we going to tell you which bond it's for? Well, the Z came for the double bond that was at carbon 2. The E occurs at the double bond that is labeled at carbon 4. In our octadiene, it's 2,4. It is the 2-ene that is Z, and the 4-ene. So clearly we've got to use numbers, and what we do is we place those numbers in brackets. We start with the lowest one first, and we say 2Z, comma, 4E, bracket, and we put a hyphen. So when there's more than one geometric isomer, we have to use numbers, commas, and letters contained in brackets to identify that geometric isomerism. Now, one last question is, if I was given the name 2Z4E 5-tert-butyl, 4-isopropyl 3-methyl octa 2,4-diene 6-ine, how on earth would I ever draw it? Well, to answer that question simply, one need only erase this structure and say, first, forget about the EZ isomerism. Just draw the molecule. How would that help you? Well, you know that EZ produces the geometric isomerism, E being opposite around the double bond and Z being on the same side. So let's just quickly, if we can, okay. There we go. Okay, so what we're going to do is say, let's say we were asked to draw that. Well, an octa, right, is 1, 2, 3, 4, 5. I'm going to need more room, aren't I? Okay, keep erasing then. And try this again. All right, let's give a little more spacing here. So, 2, 3, 4, 5, 6, 7, 8. Okay, and octa 2,4. So find the second carbon. It's there's an ene. The 4 is an ene, and 5, 6. We have a triple bond there. We have 3-methyl, 1, 2, 3. So I'm going to put a methyl here. I'm going to draw an isopropyl, carbon 4. CH, CH3. And then a tert-butyl at carbon 5. So here we go. So I do this on scrap paper. I just draw it ignoring the EZ. And then I put in my hydrogens. And I can put this H up. Okay, and there's no H's there, no H's there. And we've got this guy who must be a CH3. Fantastic. Okay, now I have to find whether I've drawn this correctly, and I can prioritize. And so I've done this on scrap paper, and I can say, okay, well, let's start with this double bond. And I'm going to say who is higher priority, the methyl or the H, and clearly carbon's higher atomic number, so around this double bond, he is higher priority. Okay, and then I'm going to say who's higher priority on this side. It's this guy. Okay, now I've drawn it linear here, but if I had tilted it down, it would be like the HCH3. In fact, the fact that the low priority HCH3 are on opposite sides here, the CH3 and this are on opposite sides. In other words, I probably should have drawn this bond up that way and this one down here, my CH3 down here. So the high priority groups are on opposite sides. So what have I drawn? I've drawn it E. Oh no. So how can I fix that? Well, when I go to draw it on my paper, I make a note, I just have to switch one side. If I switch the CH3 with the H, I've made Z. Okay? And all I have to do is exchange that. Now let's go to the other side. So if I want to fix this, I'm going to have to switch this, and I'll do that right now. I will make this guy the CH3, and I'll make this guy the H. Easy to do. So now I know I've drawn this guy Z. Let's look at the other double bond, see what we can do here. Well, let's prioritize around here. We did it last time. We did carbon, 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 hydrogen, carbon, carbon. And we discovered that this group was high priority. Right here. This group. Okay? Now, if we compare the tert-butyl to the alkyne, you will remember that we discovered that the alkyne was the highest priority. Oh, and it's a straight chain, guys, again. Well, if the low priority guys are on opposite, that means these guys in the straight chain have to be opposite the way I've drawn it. Now, I would redraw this whole structure to emphasize that and show it properly in the question. So what I'm going to do is rub this all off and draw it again for you. Pretending that this was on scrap paper. This was what I was doing on scrap paper. Remember, I'm going for 2E4Z. So now I'm going to draw my final solution on my paper. Just give myself some room. Now let's use blue. So I'm going to have a CH3 and the H. I draw it trigonal planar, make it look a little better. And this one works. Now, around this double bond, and then we have this up. Now the question is this guy on the right side? Well, we're going to have to put the CH. I'm going to just draw a CH with the CH3 twice here. Okay. Now that I've got the double bond here, and I'm definitely going to run out of room here. Okay, well, if that's the case, start over. Let's move it down a bit. Start over. Make sure I show you what I want to show you. Okay, try it again. Start with the CH3 here. CH. Double bond. CH3. I had to switch those two, and I did. Now we have the isopropyl over here. Now, is this guy E? Well, the priority groups are drawn linearly. I admit that. But if I've done these, low priority on opposite sides, it means these two must be on opposite sides. So one's down, one's up. So I want E. I've prioritized. Those two must be on opposite sides because they're the priority groups. So there I go, putting them on opposite sides. I'll put the tert-butyl here. And there you have it. I've gotten that big one and the alkyne on opposite sides, so I've drawn this E. This guy is drawn Z. Why is it Z? It looks like there's two methyls opposite each other, but the priority group was the methyl here and the monstrosity. And they're on the same side. So you see that we've drawn it Z here, we've drawn it E here. So if I was asked to draw that molecule, I would have done the black on scrap paper and then finally written out the structure thusly on the test. Well, there you have it. EZ isomerism. We've covered a lot of ground today. We've looked at isomerism, structural isomers, conformational isomers, and spent a lot of time on geometric isomers, learning first cis-trans nomenclature and then EZ nomenclature.